Chirayath. I direct the Lab for Advanced Sensing here at NASA Ames, Silicon Valley, and I wanted to share the latest progress report on our NASA NeMO-Net project. This was an ESTF2020 development that involved field campaigns and a very large CNN development for the NASA supercomputer. So NeMO-Net is the fluid lensing neural network for global coral reef assessment, and I'm here representing the entire team. As you see, Alan, Nicole, Juan, Jarrett, Sam, Sylvia, Kamuka. Actually, it was about 20 folks that got added on after that. I encourage you to check out the website afterwards. But I'm going to start with a trailer that sort of encapsulates all of the project goals and the video game that we released as part of it.
What if you could help NASA create a map of the ocean floor with just the tip of your finger? The ocean, teeming with life. It decides our blue planet, drives our ecosystems, and regulates our climate. Coral reefs are one of the most diverse and important systems in the ocean. They're also becoming an important source of medicine for some of the most deadly diseases. Dying at unprecedented rates due to rising temperatures. But we don't know how much our climate is changing. We can't until we determine how much healthy we exist now. And the only way we can know that is with your help. NASA NeMO-Net is a game where you classify the world's coral reefs by painting on real-life images into the ocean floor using a revolutionary instrument that lets us see the lethal waves at unprecedented resolution. Our oceans are so vast, it would take us 2 million years to classify the world's coral reefs by hand. The classifications you create are sent to our teams of NASA scientists at home base to teach our supercomputer to classify coral reefs on a global scale. Every contribution you make brings us closer to solving this problem. Join the NASA team to help us understand these amazing ecosystems. Take command of your research vessel and learn about all the different types of coral. We must keep the ocean alive. For life as we know it. Together, we can create a global data set of coral reefs and build a better understanding of how to save these aquatic worlds, one piece of coral at a time. Good luck, and welcome to the NASA NeMO-Net team.
So this project started with the development of an instrument that was referenced in the video called FluidCam. This was a CubeSat-based instrument that we've actually been flying on drones to generate really high-resolution pictures without refraction distortion. That's really enabled us to get a diverse perspective of reefs around the world and kind of understand what they look like as compared to what we've been doing before, which is with refraction distorted images. So here you can see a comparison between sort of the state-of-the-art prior to FluidCam on the left and fluid lensing in IntelL2. So for NeMO-Net, the question was, can we use data sets by centimeter scale data sets in different areas around the world to augment the lower resolution imagery that we get from larger global scale satellites and aircraft. And, mapping corals is really hard, not just because, the issues with remote sensing, but also they're very diverse. They typically have a biodiversity that's 100 times that of the Amazon rainforest per square meter. So developing an algorithm, a machine learning system that can separate those different species or different types is difficult in that it's just very complicated. So for NeMO-Net, we wanted to come up with an algorithm that can accomplish that and also apply a number of state-of-the-art machine learning tools to look between different sensor classes. So for number 3, you can see we wanted to implement domain transfer learning to understand how to match different spectral bands from different sensors as well as different spatial resolution scales across different sensors. Those are 2 different tasks that are typically very hard to reconcile for ocean systems because of this issue of refraction and, when a satellite has a particular view of an area. And then the final point was to generate an active learning app, which is a game that you saw to train all of that data set so that we can align them between different sensors and extract really meaningful results. So this is just a preview of the different data sources we've incorporated. So everything from FluidCam and MIDAR, which are georeference centimeter scale 3D maps, reef systems to Sentinel, Landsat, Worldview, so much coarser resolution satellite remote sensing instruments. The architecture of NeMO-Net, I won't go into too much detail because it's quite complicated, but essentially it's a fully convolutional neural network that is designed for NASA Pleiades supercomputer that runs in a UNet-style neural network, and again, we've implemented domain adaptation between the different spectral bands, as well as transfer learning to try to get between different spatial resolution bands. And typically between each sensor, there's a spatial resolution difference of an order of magnitude. So going from fluid cam to centimeter scale to the worldview at the meter scale, it's not trivial. The other thing is that CNNs need very good training data. These are all open problems right now in machine learning just for two-dimensional image processing. So we quickly realized that for these systems, you really need a three-dimensional training network that can take in all this data at very fine scales and incorporate the 3D morphology to separate out different coral classes. So in NeMO-Net, you play the game, all those results are sent to our servers at NASA. They get pooled together and compared. You can upvote or downvote different users' classifications, and this is a component of active learning. So if someone's trying to cheat the neural network by creating false entries, this is how we can, users can sort of self-regulate. And we've been really encouraged to see just a huge, just NeMO-Net launched on Earth Day this year in April, and we currently have more than 50,000 active users with 200 million views and downloads, and remarkably a good rating in the App Store, which is hard to get these days. But here you can see how well users converge in classifying corals. They're introduced to one class at a time, so they get training, and they can only progress once they reach a certain level of accuracy. And then finally, I just wanted to show some of the results by taking that really fine-scale data and using it to train lower-resolution satellite products. So this is a worldview image from Paros Banhos. Here we only have fluid cam data from a region of 2,000 kilometers away, but the morphology and the types of coral are similar enough where our transfer learning is able to classify this very accurately into multiple classes. So delving deeper into how well we're doing, we compare this to some of our collaborators at Living Oceans Foundation, who are just using an out-of-the-box machine learning system to classify their worldview imagery. And you can see that our expert classifications actually line up closer to NeMO-Net than the Living Oceans Foundation maps, and so they've actually been working with us to redo their computations using NeMO-Net. So right now for 9 classes, for example, we have an accuracy of about 84%. Prior to this, the best accuracy was around 60% using meter scale data. Comparing this to other machine learning methods, it still stands out as one of the best. It could be that we are designing it specifically for looking at multimodal spectral data, which is a big challenge, and that you have to have training data sets from each different layer that are captured by the game. So I think that's why we're outperforming a lot of the other state-of-the-art methods. So if you'd like to learn more, you can read these new publications that are out. We have a paper in IGARS coming up, as well as another special issue manuscript. You can play the game now at NeMo-Net.info, and thank you for your time.
Great, thanks so much, Vade. It's a great game. I've played it myself.